Alright, in this video we introduce the notion of uniformly continuous functions and show that any continuous function on a closed interval is also uniformly continuous. Okay, let's start. So first let us define what a uniformly continuous function is. So here's the definition. Suppose we have a function f defined on some interval I. We say this function f is uniformly continuous on this interval if the following condition is met. That is, for any epsilon that is positive, there exists some delta that is positive such that for all x and y in the interval, the following holds. If the distance between x and y is less than delta, then the difference between f of x and f of y is less than that arbitrary chosen epsilon. So that's the definition. This definition may look familiar, but it's a little bit different from the definition of ordinary continuity. Okay, for reference, let us restate what a continuous function means. So f is continuous, not uniformly continuous, continuous on this interval I, if the following holds. For any x in the interval, for any epsilon that is positive, there exists some delta that is positive, such that for all y in the interval, the following holds. The distance between x and y is less than delta implies the difference between f of x and f of y is less than epsilon. So what's the difference? The difference is here, and here. So it's where this x appears. In the case of uniform continuity, x and y both appears after this delta. So that means the value of this delta does not depend on x or y. On the other hand, in the definition of the ordinary continuity, x comes first. So that means this value of delta may depend on the value of x. So that means depending on where you are in the interval, so maybe when x is here, delta may be very small. When x is here, delta may be very large. So it may depend on the value of delta x. The value of delta may depend on the value of x. However, in the case of uniform continuous function, that cannot happen. So wherever you are in the interval, the value of delta should be constant. So if that's allowed, it's a uniform continuous function. So this uniform continuity is a lot stronger condition than ordinary continuity. So that means if a function is uniformly continuous, that implies the function is continuous in that interval, but not vice versa. So even if a function is continuous on an interval, that may not be uniformly continuous on the same interval. Okay, let's see an example. So here's an example. Consider this function f of x equals to x squared defined on the entire real axis. So this is, of course, an open interval. So it's an interval. So suppose this is uniformly continuous. So suppose f is uniformly continuous, which actually is not uniformly continuous, but we prove by contradiction. Uniformly continuous. And let's say epsilon equals to 2. Then there exists some delta such that for all x and y that are real, if the distance between x and y is less than delta, then the difference between x squared and y squared is less than epsilon. Epsilon in this case is 2, so it's less than 2. Now, for a sufficiently large natural number n, choose a natural number n such that 1 over n is less than delta. Now, we are guaranteed that this some delta exists such that this holds, right? So for that delta, let us choose a natural number n so that 1 over n is less than delta, which is always possible due to Archimedes' principle. Now, using this n, let us define x to be n plus 1 over n and y equals to n. If this function is uniformly continuous for any x and y, as long as this holds, then this should hold, right? So we can choose any x and y, whatever we like. So we choose x as this and y as this. Now, the difference between x and y is equal to, so if we subtract this from this, what we get is 1 over n, which is less than delta. Okay, now let's calculate x squared minus y squared. So x squared, so if you square this, that's n squared and 2 and 1 over n squared minus n squared. So we get 2 plus 1 over n squared, but n squared, 1 over n squared is always positive, so this is greater than 2. But that contradicts this conclusion. So it's a contradiction. Therefore, this function f of x equal to x squared, defined on the entire real axis, is not uniformly continuous. Okay, next, consider the same function f of x equals to x squared, but this time defined on a closed interval between a and b. Okay, and now we show that this is actually uniformly continuous. First, let us define a constant. Let's call it c as the maximum of a absolute value of a or the absolute value of b, and define delta to be epsilon over 2c, where epsilon is positive and that is arbitrary. Now, for any x and y that are in this interval, if x minus y, the distance between x and y, is less than delta, which is epsilon over 2c, then x squared minus y squared, if we factorize this, we have x minus y and x plus y. And this one, by assumption, this is less than delta. And this one, by using the triangle inequality, is less than the absolute value of x plus the absolute value of y, right? But due to the way we chose this constant c, both of these x and y are less than c. So this is less than or equal to c. So that is delta times 2c. But delta is actually epsilon over 2c. So that is epsilon. So that means if this is true, then this the difference between x squared and y squared is less than epsilon, whatever the value of this epsilon is, right? As long as it's positive. So that means this function, x squared defined on a closed interval, AB, between AB, is uniformly continuous. Okay, so it was not uniformly continuous, or if it was defined on the entire real axis, but it is uniformly continuous if it is restricted to a closed interval. We have just seen one example, x squared, but this observation can be generalized. That is the following theorem. It's a theorem, a continuous function on a closed interval is uniformly continuous. So let's prove it. So we prove this by contradiction. Okay, so suppose we have a function f of x defined on a closed interval between a and b is continuous, but not uniformly continuous. Uniformly continuous. Then somehow we derive some contradiction. Let's recall the definition of uniform continuity. So that was for any epsilon that is positive, there exists some delta that is positive, such that for all x and y in the interval, in this case between a and b, if the distance between x and y is less than delta, that implies the difference between f of x and f of y is less than epsilon. Okay, so now we assume that is not true. So that means we negate this statement. Okay, if we negate this statement, that is equivalent to this. So for all becomes there exists some epsilon that is positive, and there exists becomes for all. So for all delta that is positive, such that there exists some x and y in the interval, such that, so this is not true. This implies this is not true. So that the negation of that is this. The distance between x and y is less than epsilon, and this is not true. So the difference between f of x and f of y is greater than or equal to epsilon. So this should hold, by the assumption of not being uniformly continuous, we can assume this. Okay, now for each natural number n, let delta be equal to 1 over n. So, this delta can be any positive number, okay, according to our assumption. So for this, there exists some xn, yn. So these values of x and y depend on the value of n actually in the interval a and b, such that xn minus yn is less than delta, and the difference between f of x and f of y is xn, and yn here is greater than or equal to epsilon. So by this rule, we can construct a sequence of numbers, sequences of numbers, xn and yn. And in particular, note that each of x and yn are an element of this interval. So that is, so these sequences are bounded. between A and B. Now, if you there is this nice theorem called the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem that says every bounded sequence has a converging subsequence. So, according to this theorem, xn and yn, these sequences have converging subsequences. So, let x and k be a subsequence of xn converging to some value. By the way, converging values should be, of course, within the same interval. Converging to, let's say, alpha. That is, of course, between A and B. Oops, I should write subsequence of xn here. Next, by using these indices of this subsequence, we define a subsequence of yn. So using this, we can define a subsequence y and k. So this index is the same as this index, okay? But it's not guaranteed that this is a converging subsequence. But it is still bounded, so we can choose a subsequence from this subsequence. So it's a subsequence of a subsequence. And then that can be chosen so that it converges to some value between A and B, okay? A subsequence this, and from this, another subsequence, sequence is extracted that converges to some value beta that is between A and B. So it's a subsequence of a subsequence, but just by renumbering, let's call it again by the same number, same name, y and k. Okay, so this is different from this, but it's this is a subsequence of this, but just by for simplicity, we just call it like with the same name. Okay, now we have a subsequence of y that converges to some value beta in this interval. Okay, so let's summarize the situation now. So we have a sequence x and k that converges to alpha, and we have another subsequence y and k that converges to beta. Okay, and alpha and beta are of course within this interval. So that means x and k minus y and k converges to alpha minus beta. Okay, by the way, of course, n goes to infinity, and k goes to infinity. However, the definition of the sequence is this. So for each natural number n, we let delta be 1 over n, and xn and yn are chosen so that this is true. So we can assume this one. We're assuming this one actually. So we have x and k minus y and k less than 1 over n k. So this was delta. So that means we have, so as and k goes to infinity, this one converges to 0. So the difference converges to 0. So that means alpha minus beta should be equal to 0, and therefore alpha should be equal to beta. Now, since f of x is continuous, on this interval, so we have this limit nk going to infinity, f of x and k should be equal to f of alpha. And similarly, limit of nk going to infinity and f of y and k should be equal to f of beta, but beta is equal to alpha, so that is equal to f of alpha. And they're equal, of course. However, on the other hand, since f of x is not uniformly continuous by assumption, that means for any k, which is natural, so that means, of course, nk, for any nk that is natural number, we have f of x and k minus f of y and k should be greater than or equal to epsilon. Okay, that was, where is it? This assumption, right? So that means 0 is equal to f of alpha minus f of alpha. Of course, that's 0. But this is obtained as a limit of nk, actually k. It's not nk, it's k. K going to infinity of f of x and k minus f of x and y and k. But that is greater than or equal to epsilon. Okay, so this is obtained because it's f is a continuous function, and this part is obtained because f is not uniformly continuous. So, but epsilon is greater than 0. So that means 0 is greater than 0, which is a contradiction. Therefore, our assumption is not valid. So that means if f is continuous on a closed interval, then it is also uniformly continuous. And we are done. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.